So it's my pleasure to introduce Mikala Jansen again, and she will talk now about some of her own research.
Thank you. Okay, so this talk will be about some of my own research, as Peter said. So this more specifically on the stratified homotopy type of the reductive Borel-Serre compactification. So you can see that I've kind of added this little word comparison to the talk yesterday, where we talked about the Borel-Serre compactification. Also, I think there will be some repetitions for some of the local people, but I hope that's okay. Okay. So first of all, just setting the scene. So we just repeat some of the stuff from yesterday of what we're actually looking at. So we're going to look at SLNZ. This time we're going to look at a finite index neat subgroup. So if you don't know what neat means, you should think of this as being very torsion-free. The point is that I don't just need it to be torsion-free, I need various subquotients to be torsion-free. So I really need some, it's quite a bit stronger than being torsion-free. But they exist, and they exist quite in all of these kinds of groups. We have these finite index neat subgroups. Then gamma is going to act freely and properly discontinuously on the space X that we also saw yesterday. So this coset space, given by taking the real numbers or the real points of this SLN and modding out by this maximal compact subgroup, the special orthogonal group. Again, this is a smooth manifold. It's diffeomorphic to Euclidean space. So the quotient is a nice classifying space. It's a smooth manifold and the model for the classifying space of gamma. Again, this is nice. We can study this discrete group gamma using geometric tools, but we have the same problem that we had yesterday. It's not compact. So yesterday we saw one way to compactify this space, namely the Borel-Serre compactification. Today I also want to introduce the reductive Borel-Serre compactification to you. I will not be getting in, no, I'm getting kind of completely ignoring all the technicalities. So we won't see anything like a specific construction as we did yesterday. So there are several different compactifications of these spaces, and the Borel-Serre and reductive Borel-Serre are just two of these. So let me just recap the Borel-Serre, either for those of you who did not see the talk yesterday, or for those of you who would like to just be reminded what it is. So this was introduced in 73 by Borel-Serre. Today we're going to denote it like this. So I'm going to have this BS superscripts because we need to distinguish between reductive Borel-Serre and Borel-Serre. And it's a compact space. It's a smooth manifold with corners. We've introduced this corner structure in our compactification procedure. And because this inclusion identifies X mod gamma as the interior of this manifold with corners, this is a homotopy equivalence. So now we do have this compact geometric model for the classifying space of gamma. So as said yesterday, this had some very important applications. So the one we saw yesterday, and which will be used a lot this week, is Borel-Serre duality. But there are also these important calculations in algebraic K-theory relating to calculations of these K groups of the ring of integers in a number field F. So Borel showed that these calculated the ranks of these K groups, and Quillen showed that these are finitely generated very explicitly using the Borel-Serre compactification. So Borel really used this stable, calculating stable real cohomology. So kind of the low dimensional cohomology group. So not specifically what this masterclass is about, but exploiting this stability. And the idea, as we saw yesterday, was to partially compactify X and then extend the action of gamma to this partial compactification so that the quotient by this action is the Borel-Serre compactification. Okay, so this was a reminder of the Borel-Serre compactification, I need to go via this compactification to introduce the reductive Borel-Serre compactification to you. Now, for both of these spaces, the way I want to look at them is I want to look at them as stratified spaces. So I want to give you a better idea of what these spaces look like by looking at the individual strata. So to do this, we once again need to look at these parabolic subgroups. So a reminder here, a standard parabolic subgroup is a block upper triangular subgroup, something like this. So it's a subgroup in SLN. So again, we have these diagonal blocks, they can vary in size, and we have nothing below these blocks, and we have stuff going on in this corner above the blocks. A rational parabolic subgroup is a conjugate of a standard parabolic subgroup by some element in SLNZ. So these were these conjugates that I also needed yesterday. But again, like yesterday, we can, for illustrative purposes and for telling you what's going on, we can safely ignore these conjugates and just focus on these block upper triangular subgroups. I need the conjugates because I really need this action. For constructing, I need this conjugation action, and for constructing the Borel-Serre compactification, I need the orbits. I also need to compactify the orbits of these conjugates in order for things to work out. Okay, so now for stratified spaces. So by a stratified space, I mean a space equipped with a partition, a well-behaved, specify exactly what I mean by well-behaved. So these two spaces, the partial Borel-Serre compactification and the Borel-Serre compactification, are manifolds with corners, and they're naturally stratified as such, similar to what San was talking about in the previous talk. So they're naturally stratified as manifolds with corners. So more specifically, the way there's a canonical stratification of a manifold with corners given by the codimensions of the points, or the index of the points, if you like. So this translates intuitively into stratifying it by the corners and the edges and so on. So if we have this two-dimensional corner, we have a codimension 2 stratum here, which is the corner point. We have two codimension 1 strata here, which are these edges, and we have this codimension 0 stratum, which is the interior. And then in higher dimensions, you can just imagine having more corners and faces and edges and so on. So with this canonical natural stratification of the Borel-Serre compactification, the partial Borel-Serre compactification, it has a stratum for every rational parabolic subgroup P, which we denote by EP. And this is exactly the EP that we saw yesterday. So you can also see that not only do we have a natural stratification because it is a manifold with corners, but it's really constructed as a stratified space, that the whole construction is really, it's built into it that it is a stratified space. I'm not putting extra structure on this space by considering these strata. Now, what happens when I mod out by the action of gamma? So yesterday, I really more or less only talked about the partial compactification because this was the very technical aspect of it, and I didn't really consider what happened when I took the quotient. So this we'll see a bit more of that today. So when I mod out by the action of gamma, the Borel-Serre compactification has a stratum for every gamma conjugacy class of rational parabolic subgroups P. And this stratum is going to look something like this. So I'll denote it by YP. So I'm picking some representative in this conjugacy class. And this will be diffeomorphic to the quotient of EP by the action of gamma intersect P. So gamma acts on the partial Borel-Serre compactification, and gamma intersect P is going to it's going to fix this stratum EP. So we have an action on this EP, and when I mod out by this action, this is exactly what I'm left with in the Borel-Serre compactification. More importantly for this talk, this is a model for the classifying space of exactly this group. So you'll see that in now and what's followed that there's all this nice geometric structure on these spaces, and this is very important for applications and for the spaces. They have all this nice and important geometric structure, but I will just be telling you about homotopy types, because ultimately that's kind of all I'm interested in. And also I get to ignore like introducing all these technicalities to you. So I'm going to focus on what's going on in the homotopy types of these strata. Okay, so the importance of the Borel-Serre compactification, kind of the two main advantages of it are mainly the one, it preserves the homotopy type, so it's still a classifying space for gamma. And secondly, we don't introduce all these singularities. So we only introduce corner structure. We have a nice smooth manifold with corners. We don't introduce singularities in the way that kind of usually happens when we compactify. The way this is obtained is by adding enough boundary to X mod gamma. So we add enough boundary to preserve the homotopy type and to avoid singularities. However, for some purposes, it turns out that this is too much boundary. If, for example, you are interested in L2 cohomology of X mod gamma, then the Borel-Serre compactification is, in a certain sense, too big. The problem is that it does not admit partitions of unity. So here I mean L2 partitions of unity. So this means we cannot express L2 cohomology locally as sheaf cohomology. So to remedy this, Saka introduced another compactification in 1982. And what Saka did was he kind of identified that the obstruction to this square integrability, the obstruction to defining L2 partitions of unity, and got rid of this construction, collapsed this excess of boundary. So more specifically, the idea is the following. So the strata of the Borel-Serre compactification fit into fibrations like this. So we have the stratum in the Borel-Serre compactification YP as the total space. We have some base space XP, and we have a fiber NP. And I want to tell you about this fiber. So this fiber is a model for the classifying space of the following group: gamma intersect UP, where UP is the unipotent radical of P. So what is the unipotent radical? Let's just see in these examples. So if P is this block upper triangular subgroup, then UP is the subgroup of matrices where all the diagonal blocks are the identity. So I only have the identity diagonal blocks, and then I have zeros below and I have stuff going on above. So you can see if the blocks are not just size 1 blocks, then we also have some zeros above the actual diagonal, because we have identity diagonal blocks. So this is the subgroup that this fiber kind of picks out. And this is exactly the obstruction to defining L2 partitions of unity. This is getting in the way of the square integrability. So what Saka then did was simply to collapse these fibers. But of course, this means just applying these fibrations, but applying them stratum-wise. So you still need to show that applying these fibrations stratum-wise there's a nice compatibility between doing this, so that we get a nice quotient space. But this is indeed so, and the quotient space is what's now known as the reductive Borel-Serre compactification. So let me tell you a little bit about some of the applications of this space. So it was motivated by an interest in L2 cohomology, but it's come to play quite a central role in the theory of compactifications, and it has quite a lot of interesting applications. I'm just picking out 3 here, which are related to cohomology. So first of all, it's very useful for studying L2 cohomology and more generally LP cohomology. Now, it's also used to introduce something called weighted cohomology. So this is a cohomology theory on the reductive Borel-Serre compactification, defined as a complex of sheaves, so defined as a hypercohomology of a complex of sheaves. It depends on a weight parameter, so we have a whole kind of collection of cohomology theories, and it includes the usual cohomology of gamma. It also includes compactly supported cohomology of X mod gamma. So this by duality gives us homology, usual homology of gamma. Under some finite dimensionality conditions, it includes L2 cohomology of this. It also, and this is perhaps the most kind of surprising part, is that it includes intersection cohomology of a third compactification called the Bailey-Borel compactification. And the upshot of this being included is that the Bailey-Borel compactification is a very, very singular compactification where we really kind of, it's not a one-point compactification, but we're really just collapsing almost all the boundary. So here, this allows us to kind of move a cohomology theory on a very singular space, move it up to a much less singular space where it's much more easy to do calculations. So the nice thing about the reductive Borel-Serre compactifications is that we've had to introduce singularities in this procedure of moving from the Borel-Serre to the reductive Borel-Serre compactification in order to allow partitions of unity. But these, because Saka identified the obstruction to this square integrability and collapsed only this, the singularities that we've introduced are not too bad. So they're still very manageable, which means that this space is still quite amenable to calculations. Now, as a third application, and very much related, it's kind of motivated the introduction of the theory of L modules. So this is due. So this first we have LP cohomology is due to Saka, and this weighted cohomology is due to Goreski, Harder, and McPherson. And SAPER has introduced these L modules, and these are. So let me write it here. These are a combinatorial analog of constructible complexes of sheaves. So constructible complexes of sheaves, these are sheaves, complexes of sheaves, which we can use to define cohomology theories using hypercohomology. They are not necessarily locally constant. We allow a little bit more because we also allow things to be locally constant on each stratum. We don't need to be locally constant on the whole space. We can just say we just want sheaves that are locally constant on each stratum. So we're not allowing like all sheaves and like the complete kind of complication of considering all sheaves. There's still quite some rigidity in this definition, but we allow a lot more than just locally constant sheaves. So this is a nice, this gives kind of a way to study, combinatorial way of studying cohomology theories. Things like weighted cohomology and intersection cohomology. So both of these are given as hypercohomology of a constructible complex of sheaves. So I've highlighted this constructible because we'll see constructibility showing up again in a short while. Okay, so the way I wanted to look at these spaces was as stratified spaces. So what I want to do now is I want to, sorry, I keep forgetting what I'm doing here. Let me tell you about the strata I want to look at these as stratified spaces. So let me tell you about the strata of the reductive Borel-Serre compactification, and then I want to tell you that how I want to include slightly more data in just looking at each stratum individually. So the reductive Borel-Serre compactification was defined as this quotient where we applied a fibration stratum-wise. So this means that the stratification of the Borel-Serre compactification descends along this quotient map to define a natural stratification of the reductive Borel-Serre compactification. And the strata here look as follows. So we denote a stratum by XP. Again, we're picking out representatives of the conjugacy class. So if you remember, this was also how I denoted this base space of the fibration. This is just the stratum I'm left with. And this is a model for the classifying space of the following group, gamma LP, where gamma LP is the subquotient of gamma corresponding to this quotient of P, the Levi quotient, P modulo the unipotent radical. So more specifically, gamma LP is this quotient. So with these block upper triangular subgroups, what's going on? So we have this short exact sequence modding out by UP. If P looks something like this, then UP was the subgroup where we only had diagonal, identity diagonal blocks. When I mod out by this, what I'm left with is simply these diagonal blocks. So in this case, this would be a product of general linear groups and then modulo some kind of unifying determinant condition. So we can also identify this via splitting as the subgroup of matrices where I only have things going on in diagonal blocks. So I have zeros both above and below. And this sequence of groups, the short exact sequence of groups, is exactly captured by this fibration that I was applying. So the fiber NP exactly captured gamma intersect UP. YP, the stratum in the Borel-Serre compactification, captured this gamma intersect P. And what I'm left with is this subquotient of gamma corresponding to this Levy quotient LP. So just as a small remark, this is also the reason for the name reductive Borel-Serre, because this in kind of greater generality, this is done for algebraic groups. And these Levy quotients are reductive algebraic groups, which are nicely well-behaved algebraic groups, which are kind of more convenient to work with. Whereas these parabolic subgroups are in general not reductive. Okay, so as I said, I want to look at these as stratified spaces. So now I've told you what each individual strata look like, what they look like. What I want to know is also how they fit together. How do these strata fit together? But coming from the point of view of algebraic topology, I want to forget this geometric structure, which is very important for applications and for the spaces. And I want to study this using stratified homotopy theory and kind of condense, I want to just know the homotopy type of these spaces. However, in a way that takes into account the fact that they are naturally stratified spaces. So let me tell you about stratified homotopy theory, and then we'll get back to the reductive Borel-Serre compactification. So this is in various categorical levels. This is due to McPherson, Troyman, and Lurie. So just to make sure we're on the same page here, a stratified space is a topological space equipped with a well-behaved partition. So for example, we can stratify the sphere on the right here by the equator, the upper hemisphere, and the lower hemisphere. So we have these three pieces in the partition, and I call these pieces strata. Now, intuitively, you can also think of it in a different way. So instead of thinking about it as a space equipped with a partition, I can think of it as a collection of spaces or strata together with some gluing data, specifying how these different strata are glued together, how they fit together. So in this example, we have two open disks and a circle, and these two open disks are glued to the circle along some cylindrical neighborhood around the circle. So this cylindrical neighborhood would somehow be my gluing data. So given such a stratified space, I can associate to it an infinity category, which I denote like this, and it's called the exit path infinity category. So this is in every way really the analog or generalization of the fundamental infinity groupoid. So if we think of a stratified space like this as a collection of spaces together with some gluing data, then the exit path infinity category exactly encodes the homotopy type of this data. So it captures the homotopy type of each individual stratum, but crucially also gives me the homotopy type of the gluing data. So it specifies how these different homotopy types should be glued together in order to kind of recover the homotopy type of the whole space. I want to give you two examples to give you a better idea of how these exit path categories work. But first of all, I want to tell you about perhaps the kind of the most important feature of the exit path infinity category. And this is where these constructable sheaves show up again. So first of all, it's a classical result that locally constant sheaves on a sufficiently nice topological space are classified by the fundamental groupoid. So suppose here that X is just a topological space, no stratification, then locally constant sheaves on X are equivalent to representations of the fundamental groupoid of X. So this is known as the monodromy equivalence. This holds infinity categorically if I take the fundamental infinity groupoid and I take space valued sheaves, and space valued representations. And in a very, very similar way, if we have a stratified space here, then the exit path infinity category classifies constructible sheaves. So recall that constructible sheaves were sheaves that were locally constant along each stratum. Like this. So constructability, this is really the natural generalization of locally constant sheaves when I have this extra data of a stratification. In the same way, the exit path infinity category is the natural generalization of the fundamental groupoid in infinity groupoid when I have this extra data of a stratification. And it turns out that with these natural generalizations, this equivalence, this classification still holds. So this is very useful. Constructible sheaves turn up naturally when we have stratified spaces turn up naturally, and constructible sheaves turn up naturally when we have stratified spaces. It turns out that this equivalence can also be also holds if we look at the derived constructible category in certain cases at least. So we consider the usual derived category of sheaves, so complexes of sheaves, and then we mod out by these quasi-isomorphisms in the correct way. So if we could consider the full subcategory X and F. Oh, this is a very curly S. This is spaces. The infinity category of spaces. You can also replace this by any compactly generated infinity category. So if we consider the subcategory, the full subcategory, of complexes of sheaves with constructible cohomology sheaves. So this is a thing that people do. So I'm not just kind of considering this for the sake of it. The derived constructible category is important. So if you haven't seen it before and you don't want to think of exactly what the objects are here, let me just tell you that it's a source of interesting cohomology theories. So the point is that we can, as I said before when I looked at these applications, that we can, it's a source of cohomology theories where we kind of extend and take things that are not necessarily just locally constant. We have quite a few more cohomology theories, but we still have some rigidity. So we're still not taking like completely arbitrary complexes of sheaves. Now, if the exit path infinity category of our stratified space is equivalent to a one category, so the NURB of a one category, then this derived constructible category is equivalent, can be identified with a derived functor category, where I simply put in this one category. Mod R. So this gives us, I mean, sheaves can be very hard to work with because they're very like dependent on the topology. So this really gives us a point-free way of interpreting these constructible complexes of sheaves. So as I said, L modules before were a combinatorial analog of constructible complexes of sheaves on the reductive Borel-Serre compactification. A classification like this really gives like a combinatorial incarnation of these constructible complexes of sheaves. We don't just have some kind of analog where we think this is similar, but we really kind of get an equivalence of categories, an identification as a derived functor category. So we get this point-free version. Okay, so let me give you some examples of stratified spaces and in exit path categories. So in terms of objects and morphisms, you should think of the exit path infinity category as follows. So the morphisms are the points of X, sorry, the objects are the points of X. The morphisms in the fundamental infinity groupoid or in fundamental groupoid are given by arbitrary paths in the space. In the exit path infinity category, I restrict the morphisms to only consider certain paths, what I call exit paths. So in the examples that we're interested in, this means that a path can move from a low dimensional stratum into a high dimensional stratum, in a higher dimensional stratum, but it cannot go the other way. So within one stratum, it can do whatever it likes. This is also why I capture the homotopy type of each individual stratum. I really kind of include the fundamental groupoid of each stratum. But if I want to leave a stratum, if I want to move from one stratum into a different one, first of all, there's a restriction as to which strata I can move into. I can only move into higher dimensional strata. Secondly, once I've exited, I cannot return. So these non-invertible exit paths are the ones that capture the glue. So the homotopy type of the glue, they specify how do these strata fit together? How can I move from one stratum into the other? And the higher simplices are just in a certain way, stratum preserving homotopies between such exit paths, and then stratum preserving homotopies between such homotopies, etc., etc. But we'll just focus on this part. Okay, so I'm going to give you two examples where I'm stratifying the same space, the same topological space in two different ways. So you can also see the difference that the stratification makes. So we have this example from the previous slide, two slides ago, I think. So on the right, I've written the exit path infinity category up to equivalence. So we have three objects up to equivalence because the strata are path connected. We have the equator, the upper hemisphere, and the lower hemisphere. The automorphism groups capture the homotopy types of the individual strata. Now, both hemispheres are contractible, so I have no non-trivial automorphisms there. And the equator is a circle, so I just get this integer automorphism group of the green object. Now, in terms of non-invertible morphisms, I have an exit path like this from the equator into the upper hemisphere. I cannot go the other way because I've been moving from a two-dimensional stratum into a one-dimensional stratum. And likewise, I cannot go from one hemisphere to the other because I'd have to cross the equator. Now, moreover, it turns out that this path, exit path, is unique up to stratified homotopy. In fact, it's unique up to unique stratified homotopy, etc., etc. So the morphism space between these objects is contractible. So I have this up to equivalence, I have this unique morphism from the green object to the blue object. And symmetrically from the green object to the red object. I think you can kind of, if you think about this for a little while, you can kind of think how the homotopy should work. But of course, we can see higher categorical behavior. So if, for example, I stratify the two sphere like this by a point, and the rest of the space, so this punctured sphere, this open stratum, then up to equivalence, I have two objects, the point and the punctured sphere, the open stratum, because they're path connected. Again, the automorphism groups capture the homotopy types of the individual strata. Here, both are contractible, so I have no non-trivial automorphisms. And I have a non-invertible morphism like this from the point into the open stratum. I cannot go the other way. And I hope you can convince yourself that I have this kind of circle of ways of moving from the point into the open stratum. I can choose the angle with which I leave the point and move into this green stratum. And this turns out to give it rise to exactly an S1 morphism space on this side. So I have S1 worth of morphisms, or a morphism space S1 from the red object to the green object. So here, in this case, the exit path infinity category is equivalent to 2 category. Yes. So you can, yeah, so why is it S1? Why? Because, so if I take another one, so let's see if I can change the color. That's so these will in fact be homotopy equivalent, but the homotopy will be like the data of the homotopy is preserved, and that's what's in this morphism space. So the morphism space is connected. So I have one morphism, but the homotopies are in the fundamental group of the S1 is giving the homotopies between these, and then there's nothing above. and the group. It's 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 the automorphism. I mean, this is the space of automorphisms. Yeah, but I mean, you could view each integer as some kind of huge contractible thing, if you like. I can try. So the point is here that if I have another one, then I have to leave from the same point. So I'd be doing something like this. Like, there's only, yeah, exactly. There's only one homotopy there. Yeah. No. So down here, maybe I should write these down here, should perhaps like go all the way down. And then you'd kind of go around the sphere. I mean, you kind of need to think about this. Sorry. It's hard to there's an exercise about this. I've written down a lot of examples of stratified spaces that all have exit path categories equivalent to 1 categories. So you don't have to worry too much about the higher things. And then you can think about like the different homotopies. And I think in this case, you should also, yeah. I mean, to calculate this, there are explicit like short exact sequences where you think about the link and you can show exactly what's going on and identify the homotopy type of the mapping spaces. So you can do it like more formally, but to kind of understand what's going on, I think but it's, as Natalie said, there's just one here, up here, there's just one homotopy there. Whereas down here, we have kind of this flexibility of moving it around. Yeah, exactly. Yeah. So you kind of get this, you get this circle action. Yeah. Thanks. Okay, so I hope this gives you just a little bit of intuition. It might be a little bit confusing as well, but if you do want to think about this, there are 9 stratified spaces to think of in the exercise. Not today, tomorrow. Okay, so let's return to this reductive Borel-Serre compactification. So this, I should have given a warning first. This is like, I've stated the theorem in full generality. So in terms of reductive algebraic groups and stuff, but I'll don't be put off. I'll let you know what you should think of in the base case example of SLN that we're considering. So what I've done is I've determined the stratified homotopy type of the reductive Borel-Serre compactification, or its exit path infinity category. So if we have a reductive algebraic group G over the rationals, so some SLN, for example, in our case, gamma is this neat arithmetic group. So in our case, we have this finite index neat subgroup. Then the exit path infinity category of the associated reductive Borel-Serre compactification is equivalent to the nerve of a 1 category. And this 1 category is defined as follows. The objects are the rational parabolic subgroups of G. So in our case, these block upper triangular things and the conjugates. And the morphisms are given by conjugating elements. So a morphism from P to Q is an element in gamma that conjugates P into Q. But crucially, I need to mod out by an action of the unipotent radical. So I need to mod out on these conjugating elements. I need to mod out by the action of the unipotent radical by right multiplication, where I'm taking the unipotent radical of the source, the unipotent radical of P. So just to clarify, this unipotent radical is still just this subgroup where I have diagonal identity blocks. So this should really reflect the fact that in the construction of the reductive Borel-Serre compactification, I collapsed these fibers and these fibrations, and these fibers exactly captured these unipotent radicals. And composition is just given by multiplication in gamma. Now, I realized that at first sight, this might not kind of tell you very much. So I just want to highlight the two main things to take away from this theorem, if nothing else. First of all, we've determined the exit path infinity category. A priori, this really is an infinity category. But in this case, it's equivalent to a 1 category. So intuitively, it means you can kind of think of the reductive Borel-Serre compactification as a k-pi1 of stratified spaces. Its stratified homotopy type can be completely condensed or kind of encoded in a 1 category. It's not a k-pi1 in the usual sense, but in terms of its stratified homotopy type, it's encoded in this 1 category. Secondly, this 1 category is defined purely algebraically. So in terms of rational parabolic subgroups, they're unipotent radicals in this conjugation action by gamma. So in particular, it makes no reference to this space, the reductive Borel-Serre compactification. So I'm really getting a completely point-free way of studying this space if all I'm interested in is the space as a stratified space. For example, if I'm interested in constructable sheaves. So there are many applications where this really suffices, its stratified homotopy type really suffices for actually working with this space. And this is giving me a point-free way of studying it. So just as a small thing, if I don't mod out by this, then I get the stratified homotopy type of the Borel-Serre compactification. But this is perhaps a little less interesting because it's actually a k-pi1 in the usual sense, k-gamma1. So I'm not necessarily getting that much new information from that. Of a P, yes, then this, yeah, sorry. So what are the automorphisms of a parabolic subgroup P? So a parabolic subgroup is its own normalizer. So this set is going to be gamma intersect P. So here I'm just having gamma intersect P, and here I have gamma intersect UP. So it's exactly the subquotient gamma LP that I specified earlier when we looked at these homotopy types of the individual strata. So I'm recovering the correct thing for these homotopy types. Yes. It should, otherwise there'd be something wrong. But this crucially relies on the fact that a parabolic subgroup is its own normalizer. Okay, so let me give you some consequences of this theorem. Yep. The homotopy types of the strata? Yep, it's this gamma LP. So gamma intersect the homotopy type of a stratum corresponding to P is the automorphism group of P, which as Peter just asked, this is gamma intersect P modulo gamma intersect UP. So I'm recovering the homotopy type that I told you about at the beginning, the homotopy type of this base space in the fibration. So this was already known. So the point was really kind of identifying the glue and kind of figuring out how to put this into one category, a nice category. Okay, so we've determined the stratified homotopy type, but from this we can recover the actual homotopy type if we'd be interested in that. So now we're forgetting the stratification. So if I invert all morphisms in the exit path infinity category, then I recover the fundamental infinity groupoid. So you can think of this as simply saying, well, I have all these non-invertible paths in the exit path infinity category. If I invert all of those, so what I said is I can only move from a low dimensional stratum into a high dimensional stratum. Inverting that, I can move between strata however I like. So it means I can actually just recover any path in my space. So in this way, I recover the fundamental infinity groupoid. So for example, I recover the homotopy type of reductive Borel-Serre compactification. So we simply, as the kind of underlying homotopy type of this category. So this also allows me to recover a calculation of G, Merti, Saper, and Shirk of the fundamental group of the reductive Borel-Serre compactification. They do it in they use a lot of algebraic geometry. So it's the quotient of gamma by a subgroup E gamma, where this E gamma is the normal subgroup generated by the things that I've been modding out, these gamma intersect UP. So just to give you kind of some perspective on what this E gamma should be, if I have gamma all of SLN Z and n is greater than or equal to 3, then this E gamma is simply the subgroup of elementary matrices. So this E gamma is simply kind of the analog of the elementary matrices in gamma. Yep. It's normal in P, but not in C. Okay, so this is giving me the homotopy type. But as I said, I want this stratification. I want to remember the fact that I had a stratification. So I want to look at these constructible sheaves and see what do I get here. So this identification gives me an identification of the category of constructible sheaves on the reductive Borel-Serre compactification as a functor category. Like so, and this holds both 1 and infinity categorically. So it just depends on whether you think of this as a 1 category of R modules or the infinity category of R modules. And also, because it's equivalent to a 1 category, we get this identification of the derived constructible category as a derived functor category. Like this. So this is really giving me this combinatorial incarnation. Combinatorial. Of constructible complexes of sheaves. And the point here also is really using the fact that this is defined algebraically. So I get this point-free way of interpreting these constructible complexes of sheaves. So as I said, this is interesting if I want to consider different cohomology theories, like weighted or intersection cohomology. So what one would hope for is a way to really kind of a way to explore this result is to get all these point-free versions of these cohomology theories. So kind of relating this back to perhaps more to the subject of this masterclass, I think in many of the other lectures and talks, the way like using moduli spaces, we have these groups that we're interested in, and then we look at moduli spaces where we have all this extra structure that we can exploit to study these groups. What I'm doing is kind of the reverse. So I have this nice space, the reductive Borel-Serre compactification, which is really interesting. It has all this geometric structure. We have all these nice cohomology theories that are really interesting. There are many other applications. What I'm doing is I'm forgetting the space and looking at this in a point-free way, just looking at this as a category. But here, because I remember, I don't just get a group, I want to get a category because I want to remember the fact that I had a stratification. Also, it's not as I said, it's not K-pi1, so I wouldn't get a group. So what I want to do is kind of do the reverse thing and see, well, what do I get out of just considering this in a point-free way? So I'm kind of doing the opposite of exploiting these moduli spaces. As another remark relating to Sam's talk this morning, so he made this analog between this Harvey bordification and the Borel-Serre partial compactification. And then he mentioned this Deligne-Mumford compactification that we shouldn't think about. I think, so this is not completely formal, but if we think of, if we have this analog between this Harvey bordification and the Borel-Serre compactification, then the reductive Borel-Serre compactification is in some ways the analog of the Deligne-Mumford compactification. And there should be, I believe, and I believe I have the answer, I just haven't written it down. I haven't written the proof. There should be a similar identification of the stratified homotopy type, the Deligne-Mumford compactification. So the point here is that instead of just looking at these constant coefficients or kind of taking it a little bit further, looking at these locally constant coefficients, this would allow us to actually study cohomology with coefficients that are not necessarily locally constant. So we can maybe start seeing, is there anything interesting? Can we get anything interesting out of that? But these are open questions. So if someone knows that there would be something interesting to see from that, please let me know. Okay, so I just want to make a final remark, kind of just diverging completely off into another subject. Yes. So it should, is there also such a one category for the Dilly-Mumford compactification? Yes, I think it was determined by, I mean, kind of the thing I believe to be the exit path category is, no, it's this Charney-Lee, it's not stable graphs, it's this Charney-Lee category, or there is, Charney and Lee introduced a category and showed that there was a rational homology equivalence. I believe Ebert, Jansi-Okuta have since then shown that this category actually captures the homotopy type of the Dilly-Mumford compactification. But I believe it should be possible to strengthen their result and show that it's not just the homotopy type, but in fact the stratified homotopy type. So it's kind of already, the answer is already in the literature, but it should be kind of and defined very much analogously to this category that I've defined. So instead of taking the unipotent radicals, you take these subgroups generated by Dane twists and mod out by those. Okay, so let me just as a small remark at the end, I'm going to diverge off into another subject, namely algebraic K-theory. So this is just telling you how we can take this kind of point free version, this forgetting the space kind of to the extreme. So if I don't just have a point free way of studying the space, the reductive Borel-Serre compactification, but I can kind of forget that there was even a space there to begin with and just look at this category and see, well, can I generalize this category? And what do I get out of that? So I'm really kind of forgetting all these geometric origins. And let me just say that this is joint with Dustin Clausen. Then it turns out that we can, first of all, dispense with this neatness condition, this torsion-free thing. We don't really need that. That was needed in order for this space to be a nice geometric space. And instead of looking at SLN, we now consider the general linear group. So we get this nice category, which I will denote like this now instead, C and RBS instead. And now it turns out that with just a small translation of the definition, so this is defined completely verbatim. There's no the definition is completely the same. A small translation of this definition into a kind of a slightly different language in terms of flags and things means that we can define it for an arbitrary ring, an arbitrary associative ring. So we get this C and RBS of R. And this category turns out to fit nicely, at least its geometric realization, fits nicely into this sequence. So it factorizes this natural map between the classifying space of GLN of R and the K-theory space associated to R. And this is a way to define unstable algebraic K-theory. So this unstable referring to the fact that I'm fixing the N. So it's kind of a way of approximating the K-theory space for fixed N. You could think of it like this. And this model for unstable algebraic K-theory, just to finish off, this is very vague, shows some promising properties in the kind of the small investigations that we've done there so far. So it's just telling you how you can take this kind of forgetting the space to the extreme and move into kind of a completely different area. But this doesn't have much to do with cohomology. I just wanted to add it because it's fun. And that finishes my talk. Thank you.
Can you hear me on Zoom?
Yes, yes. Okay. Was there a reason to believe that the stratified homotopy type should be a one category? Morally? For Dustin? I don't know. For me, Dustin. Are there interesting structures on this one category that one could exploit to do calculations? I mean, as the one category as it is, no. But I believe that, I mean, I'm working on this kind of identifying these. So we have this identification of the derived constructible category as a derived function category. But I mean, this is an equivalence, and it's not completely obvious how to actually do the translation. So I'm working on identifying these cohomology theories, these constructible complexes of sheaves in the point-free interpretation. And some of these cohomology theories really exploit kind of this algebraic group structure, or the fact that we have some Lie algebra stuff, or some geometry. They exploit some of this to get some weight decompositions or character decompositions. So it might be necessary or relevant to kind of to maybe take a version of this one category where we have kind of an enriched version, maybe in algebraic groups, or in to get some more structure that we can employ. So it exploits that we get this weighted cohomology, as kind of is suggested, really kind of uses actual weights, and I can't do that in kind of incomplete generality. So one might be, it's kind of, yeah, it's a possibility, and maybe also necessary in some applications to actually kind of do something to this one category to equip it with some extra structure. Yes, so the question is it true also for the Borel-Serre compactification that its stratified homotopy type is a one category? Yes, and the one category is kind of exactly what you see here, except that you don't mod out by this action. So the morphisms are just actual kind of transporters. Like identifying exit path categories. I mean, I have a general, sorry, if I've tried other examples of stratified spaces for exit path categories, more specifically a quotient, I think by something. So I have a general theorem for identifying stratified space, exit path infinity categories of kind of nice enough quotients. Yeah.
Any questions? So,
Okay.